Hi everyone, we are Group 12 and today we'll be presenting on our supervised learning project based on the Titanic survival dataset. The aim of this task is to build a predictive model that estimates whether a passenger survived or not based on attributes such as age, sex, ticket class, fare, family size, and cabin information. The dataset provides labeled training data, allowing us to perform binary classification using standard ML techniques. The analytical value lies in understanding which passenger characteristics most strongly relate to survival and in building a robust model that generalizes well to unseen passengers in the test set. The training dataset contains 891 passengers with a binary target variable survived. The test dataset includes the same input features but without labels, so the final model must generate predictions. Before modeling, we examine the class balance. The positive class, passengers who survived, has a rate of 38.4%, while the negative class is 61.6%, resulting in a negative-positive ratio of 1.61. This indicates mild imbalance, but still within a reasonable range, so we decided not to oversample using smooth Tomac for the main model pipeline, relying instead on model capacity and class weights. This conclusion is also shown visually through the distribution plots before and after the balancing check. To ensure consistent and clean input for the models, we built a pre-processing pipeline using column transformer and scikit-learn pipelines. For numerical columns, we applied median imputation, a distribution transformer, and standard scaling. For categorical features, we used most frequent imputation and one-hot encoding. To improve model robustness, the encoder automatically handles unknown categories. Next, we engineered several features to improve signal for the model. From the passenger names, we extracted title normalized into groups such as royal, officer, miss, mrs, and so on. We computed family size and derived is alone, which is meaningful because traveling alone significantly affects survival probability. For ticket and cabin information, we extracted ticket prefix and cabin deck, both of which captures socioeconomic patterns. Fare and age were adjusted by computing fare per person, log transforms, and interactions such as age with P-class. These engineered features were then fed into the pre-processing pipeline and model training. Here are a few concrete examples of how the raw data was transformed. From a name like Braun, Mr. Owen, we extracted the title Mr. and mapped it to a standardized category. Using sibling spouse and parent children, we compute family size and determine whether the passenger is alone. A ticket such as PC17599 is simplified to a ticket prefix, and a cabin like C85 use the deck C. And for fares, we create fare per person and apply log transforms to stabilize skew. These examples illustrate how we convert messy raw text and numerical fields into structured signals that models can learn from.
Our first model, logistic regression, was chosen as a vital linear baseline. It is fast, highly interpretable, and serves as our benchmark for the more complex ensemble methods. We intentionally optimized this model using grid search CV with the scoring matrix set to recall. This was a strategic decision, as in survival prediction, maximizing true positive where we correctly identify survivors is a critical safety and business priority. The tuning process explores a wide range of regularization strengths, both L1 and L2 penalties, along with class weights. The grid search was successful, yielding a strong result. The best configuration utilized L1 regularization and applied balanced class weights to counter the 1.61 imbalance ratio. This resulted in the highest recall score among all models we tested, achieving a best cross-validation recall of 0.8216. The simple, highly tuned linear model, specifically focused on the recall matrix, proved to be the most effective at identifying the positive class. Next, we implemented the random forest classifier, an ensemble method known for its ability to capture non-linear relationships and resistance to overfitting. We expected this model to leverage the complexity of our engineered features like title and family size. The random forest tuning explored a much larger grid, focusing on parameters like the number of trees and the complexity of each tree. We also strategically tested balanced subsample for class weighting, which applies weights to each individual tree's bootstrap sample. The best random forest model had a moderate complexity, using 400 estimators and a max depth of 10. However, when optimized for recall, it achieved a slightly lower best cross-validation recall of 0.8041.
Next, I'll discuss the XGBoost model, which ultimately gave us a cross-validated recall of 0.7543. We chose XGBoost because it naturally handles nonlinear relationships, offers strong built-in regularization, and uses boosting. which focuses the model on correcting the hard-to-predict cases. After tuning, the best hyperparameters we found for XGBoost are as shown. Firstly, the learning rate is found to be relatively small, which forces the model to learn gradually, and this reduces overfitting and stabilizes training, especially with boosting. And next, we set the number of estimators to be 500. Because the learning rate is small, we compensate by using more trees, and 500 trees is enough to capture patterns while still preventing overfitting. Next, we set the max depth to 3, where using the shallow trees prevent the model from memorizing noise in the data. Next, I'll explain the evaluation metrics, where we use two recall and the ROC-AUC curve. Firstly, recall is especially important for the Titanic's survivor prediction task. In our dataset, the positive class is the minority at around 38%, and recall measures how many actual survivors we correctly identify using the formula recall equals to TP divided by TP plus Fn. A high recall means that the model is missing fewer actual survivors. This is crucial because conceptually a false negative, for example predicting a survivor as non-survivor, is more costly than a false positive. So, prioritizing recall helps us to reduce the chance of overlooking survivors and mitigate the effects of class imbalance. The second metric we rely on is the ROC-AUC curve, which is completely threshold independent. Instead of evaluating the model at a fixed cutoff like 0.5, the ROC-AUC curve looks at all possible probability thresholds and measures how well the model separates the two classes. So the curve complements recall, where recall measures the model ability to catch survivors, while ROC-AUC measures its ability to separate survivors from non-survivors at a global level. So when we look at the results, we see that the logistic regression achieves the highest recall at 0.8216, while the random forest achieves the highest area under the curve at 0.880. However, overall we find that random forest performs the best because it ranks highest for the area under the curve while still maintaining a high enough recall at 0.8041. This model strikes the best balance between detecting survivors and ranking the predictions accurately, making it the most reliable overall choice for the task. With this, I end the presentation and feel free to ask any questions.